Hello everyone, my name is Bhavana SP and I am currently studying in AML first year. Our team members are Bhavana Patil, Hemant D, Chetan Gupta. Today I am here to explain the circuit of BJT. Transistors are introduction. Transistors are fundamental semiconducting components widely used to amplify, switch, and control electrical signals in electronic circuits. One of the simplest and most instructive configuration is the transistor as a switch, which forms the backbone of digital logic and automation systems. In this circuit, a bipolar junction transistor is used to control the on or off state of an LED based on the input from a push button. This experiment aims to offer practical exposure to both circuit construction and the operating principles of transistor switching, which are core concepts in electronics and embedded system design. Next abstract. This experimental investigate the application of BJT as a solid state switch by designing and simulating a circuit that turns an LED on or off using a manual switch. The circuit consists of a DC voltage source, a resistor, a push button, an NPN transistor, and an LED connected to form a classic transistor switch configuration. The push button controls the transistor's base, allowing users to observe saturation and cutoff modes. The study demonstrates how transistors enable automated control of higher current devices using low current signals, offering insights applicable to real world electronics and digital logic.
Now I am going to say the objectives of the BGT to demonstrate how the BGT can function as an electronic switch, to design and stimulate a circuit that controls an LED using a transistor and push-on, to understand transistor operating regions, cutoff or saturation, and current amplification, to correlate experimental results with theoretical switching behavior in digital circuits. Now I am going to explain the methodology of BJT. Assemble a circuit that consists of a 12-volt DC supply, a 1 kilo ohm base resistor as R1, a push button switch S1, and a NPN BJT and an LED in series with a collector. The push button and resistor connect to the transistor base. When pressed, S1 allows a small base current which controls a larger collector emitter current. In the off state, means switch unpressed, no base current is passed. The transistor remains in cutoff and the LED is off. When switch is pressed, the base emitter junction receives sufficient voltage to turn the transistor on, means that is saturation mode. Allowing current to flow from collector to the emitter means lighting the LED. Analyze and record the voltage drops and current flow in both on-off and state to confirm the expected operation.
To conclude this simulation, the simulation confirmed that the BJT operates efficiently as a switch for controlling an LED. When a sufficient base current is applied by the push button, the transistor enters saturation and enable current to flow through it. Light it up. Otherwise, the LED remains off, corresponding to the transistor cutoff region. The experiment validates the principle the small input current at the base can control much larger current through the collector emitter path, making transition vital for digital control, logic circuits, and automation tasks in electronics. ಹಲೋ ಸ್ಟಾಪ್ ಮಾಡಿದ್ರೆ ಒಂದು ಸ್ವಲ್ಪ ವಿಡಿಯೋ ರೆಕಾರ್ಡಿಂಗ್ ಸ್ಟಾಪ್.
Next topic, summing amplifier. Introduction. A differential amplifier is a fundamental building block in analog electronics, especially in measurement and instrumentation applications. Its main function is to amplify the difference between two input signals while rejecting any voltage that is common to both inputs. The, this property makes it very valuable in environments where noise or interference is present, as coming mode noise is suppressed, allowing only the useful signal difference to be amplified. The circuit in the image features an operational amplifier arranged with equal resistor values in a classic differential configuration. Abstract. This simulated circuit demonstrates a differential amplifier using an ideal op-amp and precision resistors. The input side receives a 10-volt source divided equally between two nodes through two 1 kilo ohm resistors, thus presenting identical voltages 5 volt to both the inverting and non-inverting terminals of the op-amp. The output is taken after a feedback resistor, also 1 kilo ohm, and the simulation shows the expected near zero output voltage when both inputs are the same. This validates the circuit's ability to reject common mode signals essential for accurate signal processing in noisy environments.
I am going to say the problem statement of summing up amplifier. In practical electronic systems, signals of interest are often contaminated by unwanted noise or interference that appears identically on both lines. Common mode noise. When amplifying a small signals, it becomes crucial to reject this noise and accurately amplify only the difference input signals. The problem addressed by this experiment is to design, stimulate, and analyze a differential amplifier that demonstrates high common mode rejection and outputs only the differential component, thereby improving the robustness and precision of analog measurements. Now I am going to say the objectives of this project. To design a differential amplifier using an operational amplifier and same value resistors, ensuring balanced input path for common mode rejection. To validate the behavior of the differential amplifier by applying identical voltages to both inputs and confirming a zero for or a non-zero output, illustrating noise suppression capability. To understand the significance of resistor matching and feedback in maintaining amplifier performance and accuracy. To analyze the stimulation outcome and verify the observed results align with theoretical expectations of differential amplifier operation.
Application of this circuit are it kind of conversion analog sensor signal conditioning where interference must be rejected, audio electronics to eliminate hum and noise picked up by cables, data acquisition system require precision amplification of small differential signals while ignoring the noise. To conclude this topic, the simulated differential amplifier circuit demonstrates the principle of common mode rejection, the producing almost output when both inputs were equal, that confirm correct design and theoretical operations. Such findings reinforce the value of differential amplifiers in applications where signal integrity and noise immunity are crucial. The experiment highlights the importance of matched resistor and feedback for achieving reliable performance. The circuit serves as an excellent fundamental example for engineering students entering into analog design.